Right. Thanks, everybody. Here we are for the BSEC research chat on biogeochemistry, a theme that, as we know, has always been called biogeochemistry and always will be called biogeochemistry and never would have had any other name. So, gonna hand it over to Professor Scott Miller to kick us off. Go ahead, Scott.
It sounds great. So thanks everyone for joining for the biochem geochemistry research chats. Instead of sort of me giving a big overarching presentation and butchering the details of everyone's work, we figured we'd have a couple different presentations from people at Hopkins and also Penn State talking about different aspects of biogeochemistry work that's been happening. So I think we'll kick it off and have Sam Murphy talk about some of the work with eddy flux towers and other work from Ken Davis's group. And then Gabrielle is going to talk about some of I think, the ecosystem level measurements that the folks at Penn State have been making and elsewhere. And then we'll finish off with Chulin Lee, who's a PhD student in my group at Johns Hopkins and co-advised by Kirsten Kohler. And she's going to talk about some of the work she's been doing with the low cost air quality sensor network here in Baltimore. So hopefully that was a good and quick introduction to everyone. And maybe I will turn it over to you, Sam, if that sounds good, if you want to kick things off and talk about some of your research.
Yeah, that sounds great. I'm gonna share my screen and let's see. Do you see PowerPoint in full screen now?
Yep.
Yes, I do. Looks
Okay,
great.
good. Yay. Okay, I'm just gonna make Zoom small. Okay, so thanks for having me today. So, my name is Sam. I'm a PhD student working with Ken Davis at Penn State. And I'm actually kind of new to working with the BSEC data. I largely have been working on greenhouse gas fluxes in Indianapolis, but I'm excited to share some of the measurements of greenhouse gas fluxes from neighborhoods in Baltimore today. Okay, so starting off with some sort of background, big picture. So, urban vegetation and human behavior both contribute to the exchange of greenhouse gases between the surface and the atmosphere, which I'll refer to as the flux. And so, through behavior like driving cars and heating buildings, we emit greenhouse gases into the atmosphere as humans. And then here, this figure is showing the one of the areas around one of the Baltimore flux towers. And so, in a relatively small area, we have both major roadways and minor roadways where cars are driving and emitting fossil fuels and or burning fossil fuels and emitting greenhouse gases, as well as different types of vegetation like trees and turf grass, all close together. So, we really want to be able to understand the sources and sinks of these greenhouse gases in cities that are quite complicated. But one of the ways that we can do that is through the use of eddy covariance flux towers, which provide direct and continuous observations of greenhouse gas fluxes at high space and time resolutions. And when I say high space and time, I'm talking about hourly to 30-minute time measurements, and then also about neighborhood scales in the spatial dimension. And over here on the right, I have a representation of a flux tower footprint for an urban flux tower. Actually, this one is in Indianapolis, not in Baltimore. But I really like this figure. And when I say footprint, I mean the surface area that we see with our flux tower. So, what is the surface area that's impacting our flux measurement? And typically, with these towers, we are able to see about a kilometer to a few kilometers around the tower. And now I'll get into a little bit of the actual measurements in Baltimore itself. So here is a map of Baltimore, and a lot of you may be familiar with these measurements already, but I'll just do a quick summary. So the ones I want to point out here are these three red triangles are the three BSEC flux towers that I'm going to be talking about today. So these are the Howard Park, the Broadway East, and the Lake Clifton flux towers, where the Howard Park and Broadway East are over sort of a residential mixed landscape and the Lake Clifton Flux Tower is measuring turf grass. And then a couple other measurement sites that I want to point out are locations of these NIST concentration or mole fraction towers. So these four towers that I'm pointing out here are locations of greenhouse gas mole fraction measurements. And I'll come back to these a little bit more later in the talk, but I want to show a little bit more details about the BSEC flux towers first. And so these three figures here are the Howard Park, the Broadway East, and the Lake Clifton flux towers. And this is just sort of the satellite imagery of the area surrounding them. And so, as I mentioned, Lake Clifton is focused on measuring turf grass. So it's sort of just located in this turf grass field, while the Broadway East and Howard Park towers are located within residential neighborhoods, where Howard Park is located, I think, in a bit of a higher income neighborhood where most of the homes are single family homes. And then Broadway East is located in a neighborhood where most of the homes are row homes. And just to give you an idea, if you don't know, these flux towers, so both Broadway East and Howard Park, are the instruments are mounted on just existing cell phone towers. So this is the Broadway East Tower, just to give you an idea of what it looks like. And then the Lake Clifton Flux Tower is, we call these shorter stature towers. They're closer to the ground because we're not looking to see as large of a surface area with this tower. And this is the Lake Clifton Tower, along with Ben Allswede and Ying Pan from Penn State. So getting into some of the actual flux results. So first I'll go over a little bit of conventions that we use when we talk about flux measurements. So this figure here is a 6-month time series of CO2 flux measurements from the Howard Park flux site. Um, and so the CO2 flux is represented as the CO2 exchanged per unit area per unit time. And each of these points is a 30-minute measurement that you see here. And then one more convention is that the positive values are CO2 into the atmosphere, and the negative values are CO2 into the surface. And a little bit of background before I show some more results. So plants remove CO2 from the atmosphere when they grow through the process of photosynthesis, and they release CO2 into the atmosphere when they respire, same as how when we breathe out, we release CO2. And so when we have this flux tower, we're seeing both the removal of CO2 and the release of CO2 from plants, and also the release of CO2 from microbes. And so here are some of the results from this turfgrass tower. And so this is the CO2 flux and then time on the x-axis. And what I really want to point out here is that the seasonal pattern of fluxes that we see is really tied directly to what we would expect from the vegetation. So we see that during the summertime months, we see larger levels of drawdown. And then during the wintertime months, we see smaller levels of CO2 drawdown. And that's because during the warmer months, there's increased levels of photosynthesis. And another way we really like to visualize these CO2 fluxes is by looking at what an average day looks like. So this figure here is showing the CO2 flux on the Y again, and then on the x-axis we have time of day, and each of these lines represents the average day for a different season. So blue is winter, red is fall, green is summer, and orange is spring. And there's a lot of interesting stuff that we could chat about this figure, but what I want to point out is that on average, we see that the CO2 drawdown is largest during the spring and smallest during the winter time, which is pretty much what we would expect from vegetation. And now, before I get into some of the results from the residential neighborhood flux towers, I just want to talk a little bit more about some background. So, we emit CO2 into the atmosphere when we burn fossil fuels through activities like driving your car or if you heat your home with natural gas. So when we measure CO2 fluxes in a neighborhood, we expect to see a mixture of fluxes from both human activities and also biological activities. So here I'm showing a similar plot where this panel on the left here is the Howard site and the right panel is Broadway. And this is the median CO2 flux by hour of day for the different months that we have. These are all observations from 2025, so July through December. And what we expect is that fossil fuel emissions are positive at all times, and then biological fluxes are negative during the daytime and positive at nighttime. So we expect to be seeing a mixture of these things at these sites. And what I want to point out here is that over the course of the day at either of these sites, vegetation does not offset human emissions because the flux is only actually negative for a few midday hours during the warm season. And then, for example, during November and December at the Howard site, it's never negative. And we can learn more about what the local sources of these emissions are by looking at the spatial variation of these fluxes. So here I've plotted the average CO2 flux binned by 45-degree wind directions at the Howard site for June, July, and August, so the warm season in this top panel, and October, November, December, so the cool season in this bottom panel. And there's a couple interesting things that I want to point out. First, that a significant proportion of the CO2 emissions appear to be from the nearby roadway direction, so this major road here during the summertime. And then during the wintertime, we see that a lot of the wind directions have larger emissions compared to the summertime. And we think this is probably due to the additional emissions from home heating. So we can learn a lot just from this sort of simple evaluation of the average fluxes by wind direction. And so now I'll show some results from the methane emission side. And so first, a little bit of background. Methane is the main component of natural gas, which is the fuel that we use to heat homes and run appliances like stoves. And this methane, when we use it in our homes, can escape into the atmosphere from either leaks in pipelines or directly from appliances. And we care about this because methane is a powerful natural gas, and we also don't have a lot of good information about how much methane is actually getting into the atmosphere because leaks aren't reported. So we really need to rely on observations like these to learn about the emissions of methane. So I want to show some results that are actually not from the Baltimore flux towers, but are using those mole fraction or concentration towers in the NIST network that I mentioned earlier. And these results were created by a colleague of mine who recently graduated, Helen Kenyon. And so this figure here is showing the average excuse me, not CO2 flux, the average methane flux for month of the year for these different sites. So each of these lines is a different site. And these orange and red sites are urban, and these blue sites are suburban, and these gray sites are rural. So what we learned from this is that the methane emissions are highest inside the city and also during the winter time. And she also looked at how the methane flux varies across time of day. So these two panels are two different sites, and the green line is the methane flux across time of day, and the blue line is the natural gas usage for time of day. And so we see that the methane emissions seem to be closely related to gas usage in the city. And so this tells us that some of the emissions of methane are not coming from leaks in the distribution lines, but instead are coming from homes and businesses. So this is really important for guiding any mitigation efforts that we might suggest based on these measurements. And I also want to point out that this relationship between gas usage and methane emissions holds across seasons. So these are the same two sites, so that were shown in the previous panel, so this panel. But now it's split up by winter, fall and spring, and summertime. And this appears to be a similar relationship between the gas usage and the actual methane emissions that we see. And so now coming back to the BSEC towers, here I'm showing the average methane flux that we observe by 45-degree wind bins again for the warm season and then the cool season at Howard. And I want to point out that in the wintertime, especially, we see higher emissions from these particular directions. And we think these could be potential leaks in the distribution system. And so the looking at these spatial patterns can help us identify sources and suggest mitigation efforts to potentially eliminate leaks. And so just to kind of sum up, a lot can be learned from these flux tower data. I think we're already learning a lot even from a pretty preliminary analysis and only 6 months of data. For example, we've seen differences in the temporal patterns between sites. We've seen spatial patterns that might suggest particular types of emission sources. And in the future, I think it could be cool to focus on using some of the additional data that BSEC has to separate biological and fossil fuel fluxes in those residential neighborhoods. But sadly, these urban flux towers were actually just decommissioned this week. So we'll have an additional 6 months of data compared to what I showed you here, but that we'll only have that 1 year. So that's a little bit sad. But on that note, I'll just say thank you, and I'm happy to take any questions.
Awesome.
I'm gonna stop sharing so I can
Great
see you.
that's a great presentation, Sam. It's fun to hear more about some of the recent results from the Flux Towers. Um, does anyone on the call have any questions for Sam before we pivot over to Gabrielle? Any any other questions? I'm still I was just gonna say that I'm still very impressed with both the Flux Towers and then the NIST towers, like the extent to which you're able to parse out differences in methane fluxes. Like I would not have guessed that you'd be able to parse out the suburbs versus the city so well, like in Helen's work from those NIST sites. And I think it's really cool that you see those spatial and seasonal patterns.
Yeah, it's so stark in those, like how different the different regions are in that plot.
Mm-hmm.
I think Ken mentioned in the chat um the BG&E data gas usage data. I think we're supposed to maybe be getting some of that data for the uh BSEC flux tower sites, and that will be really cool to see um if the gas usage data, if we see a similar trend in the BSEC flux towers.
Mm-hmm. Yeah, yeah, that'd be
Yeah.
neat as well.
The
Cool.
other,
Well,
the other difference I would note there, Scott, is that we're not using an inversion
mm-hmm, mm-hmm, mm-hmm,
where you look at a larger scale integral. The
mm-hmm.
micromet methods are much more local. And God, did we have a fight over that in the Elementa paper that Helen Kenyon published.
Okay.
A reviewer just did not want to accept that. We eventually won.
Sounds like you have some battle scars from recent reviews.
Oh man, that was a tough one. But
Um,
it sees locally, so you can really see these local patterns. You don't get the whole city though.
yeah. Cool. Well, anyway, super impressive work, Sam. Fun to hear about it.
Yeah,
Maybe
thank
with
you.
that, unless we've got other questions, we'll pivot over to Gabrielle.
Can I
And
just
do you want
ask
to?
a quick one?
Oh yeah,
This is
Jonathan, go for it,
John.
John.
That was awesome, Sam. Thank you so much. Would you mind bringing back up that CO2 flux slide again?
Yeah.
Which one, John?
The one that you commented on with the
The grass?
large uptake,
The grass.
the grass ones.
Uh, this one?
Two up,
That
I think.
one.
Did you want that one or did you want
Yeah,
the
that one is because that is tower derived, right? The smooth lines.
it's just
Yeah, these are just the
Nice.
averages for each season.
Got it. So, yeah, this is really interesting. As I think you're about to see, Gabrielle didn't see this from the chambers. And so, are we looking in different types of grasses, lawns?
Oh.
But yeah, it's really interesting because those are very negative.
Oh yeah, it's a very large negative, negative 20 micromoles per square meter per second.
on
Yeah,
average.
Mm.
average.
Yeah,
That's huge.
yeah. But
Right.
And
even
Gabrielle's
for
chambers,
any,
Gabrielle's chambers are dark, right? Aren't they, John?
What's that?
I mean, this is photosynthesis taking up the CO2.
Yeah.
And Gabrielle's chambers, aren't they dark?
I mean, they are
Yeah. So I
opaque,
mean,
but
there is
they're,
the
oh,
smart
sorry.
chamber over it, which is,
Big.
but
But there's no light, right? So I mean,
yeah.
I've been
But
measuring
it's
CO2 fluxes from grass chambers for a long time, and I constantly struggle with the plants are just they're all fixated on light. It's a big deal for them.
it is opaque, but I think because it's only on there for the 2-minute timestamp, I would think it wouldn't have a large impact.
I don't know.
Yeah.
No
Photosynthesis
photons.
Mm.
turns off instantly.
No
Yeah.
photons. No action, I think.
So that explains
Okay.
that explains the difference between the tower and the chambers.
Thanks. But it is interesting to see those. It really does put it, and then the timing, right? The day of, when you actually go out to measure. Again, we opted not to do the automated chambers that have some light transmission through them, just because they're a favorite of target practice for suburban teens. But all right, thank you very much, Sam. That was great.
Yeah, thank you.
Awesome. Well, let's pivot over to Gabrielle, and do you want to take it away?
Yes, I can share my screen really quickly. Let me see about getting this in full screen. Okay. I think it's loaded. Can you see it full screen?
Yep,
Yeah.
looks great to me.
Okay, excellent. Awesome. So thank you all for joining me here today. I'll just be discussing my master's thesis research on quantifying the spatial and temporal variability of biogenic greenhouse gas emissions in suburban Baltimore. So to start, we're looking at the carbon and nitrogen cycle inputs and how those are transformed in the soil into greenhouse gas flux. So primarily focusing on carbon and nitrogen that will enter the soil and then be microbially transformed into carbon dioxide, nitrous oxide, and methane. And we are focused on three main biogeochemical processes. Carbon dioxide is associated with soil respiration. Methane is associated with methanogenesis and methane uptake. And then nitrous oxides associated with both nitrification and denitrification. And as you guys know, these are microbially mediated processes. So we are concerned with different soil parameters such as soil temperature, soil electrical conductivity, and then soil moisture as well, and how that impacts these communities and may influence the degree to which we're seeing this biogenic flux coming out of the soils. So primarily suburban landscapes have been understudied. So that is the research gap that we're targeting with this. Most greenhouse gas studies have focused on either the urban core, where you're seeing these large anthropogenic inputs, or more rural natural ecosystems in which biogenic fluxes may be much more significant. But this kind of leaves a suburban blind spot in the research. Which is unfortunate as these are unique environments, being inherently heterogeneous because they represent a diverse mosaic of landscape types. And then also this suburban ecosystems are rapidly growing as exurban areas or urban areas move into exurban areas and more rural areas and rapidly are transforming these land covers. And so what we're concerned with are biogeochemical hotspots and hot moments and trying to quantify those. Our research is primarily focused on the spatial end of things, looking at hot moments. McLean et al. In 2003 defined these as patches that show disproportionately high reaction rates relative to the surrounding matrix. A common example of this in the literature could be a riparian zone, where you'd see high organic matter content and more anoxic conditions that could contribute to higher fluxes of a certain greenhouse gas like methane. And the research objectives we have for the study are to, one, quantify the spatial variability of carbon dioxide, methane, and nitrous oxide across 4 dominant suburban land cover types. We're focused on lawns, forests, a stormwater detention pond, and riparian zones. So really including both built and natural elements that are found within suburban ecosystems. And then secondly, we want to quantify the contribution of different land cover types and upscale to the watershed level greenhouse gas emissions with consideration of variability in the fluxes. So the watershed that we're focused on for this study is Dead Run 5. It is a subset of the larger Dead Run watershed, which in turn is a subset of the larger Gwynns Falls watershed. Dead Run is about 14 square kilometers, and Dead Run 5 sits within that. It is located just outside of Baltimore city boundary lines in Catonsville, Maryland. And here on a pie chart, I have the land use types parsed out. So you can see that in this watershed, residential lawns dominate, followed by riparian zones, and then the forest exterior and the small urban forest interior patch. And then finally, our stormwater pond is the covers the least amount of spatial extent. And as you can see, we have 11 sampling sites across the whole. We have sorry, you guys are kind of covering my screen. Yeah, we have the riparian brush, riparian lawn, restored floodplain, and the stormwater swale and forest and size sites are our riparian sites. And then we also have a forest exterior and interior site that represents our forest land type. And then we have Westview Park Lawn and Winters Lane Lawn as our lawns. And then finally, both the pond and the pond bank as our pond type. So we've been using the Lycor trace gas analyzers, both the 7810 and the 7820 units. With this, we can measure carbon dioxide and methane with the 7810 and nitrous oxide with the 7820. This is coupled with the smart chamber, and this is which we have 11 of these, or as mentioned previously, we have 11 sites across the watershed with 3 to 4 replicates. And these PVC collars right here in the upper left-hand corner represent our replicates in the study. They're about 8 inches in diameter, and it is atop this which the smart chamber will sit. And this will close here when you get a measurement. And it's about a 2-minute timestamp. And then additionally, we have the smart chamber it comes equipped with a Stevens hydroprobe. And this is what we use to get real-time measurements of soil moisture, electrical conductivity, and soil temperature. Also up here in the right-hand corner, we have a floating chamber design. And this was piloted by Geckner et al. And this is what we use to get the over water flux measurements in addition to the over soil measurements. So we've been going about once a month to get these measurements, trying to target about mid-month so conditions are constant, and 1 day to ensure consistent biogeochemical conditions. And then also over the summer, we did do some storm sampling about 1 to 3 days after an event. But I'll be focusing on looking at our monthly sampling for the purposes of this talk. So just some results from our study. So for carbon dioxide, we were able to find that the highest fluxes were from the forested and size sites and the lawns, and there was slightly more variability in riparian sites. So here you can see on the right-hand side, we have our seasons. So each of these dots represents a point taken during a certain season. So we have fall, spring, summer, and winter. And on the left-hand side, you can see the flux in micromoles, meters squared per second. And then also whether the arrows dictate whether something was acting as a source or a sink. And then down here on the x-axis, you can see which site corresponds to which land cover type overall. So we found that we got the highest amount of fluxes in the summertime for carbon dioxide. And carbon dioxide as a greenhouse gas primarily acted as a source throughout the whole of the study. We only had a few points that actually were negative. And we additionally saw the lowest points in the winter. So we found that this greenhouse gas was the most influenced by environmental conditions. And it especially was influenced by air temperature and soil temperature, which is consistent with the literature. It did have somewhat of a weak relationship with soil moisture. I think it tended to prefer, or you tended to see higher fluxes from the more upland, drier sites, as opposed to the more heavily saturated sites like the pond or the pond bank. And then for methane, in general, opposed to carbon dioxide, we found methane to be a moisture-loving greenhouse gas. So we saw the highest fluxes here from the most saturated sites. So the pond had the highest fluxes overall in the study, along with the pond bank, and also the stormwater swale and restored floodplain. And these were our most consistently saturated sites, and they also had the most hydrologic connectivity overall. It is interesting because the forested and site tended to fall more in line with some of our more upland sites. And I think this may be because these sites are more heavily incised. So they're not as connected to the waterways as some of the others. And then in terms of seasonality, we saw some high methane fluxes in summer and spring, so where you're getting moist, slightly warm conditions. But we did also see methane uptake in summer. So it shows that as the soils become drier, methane uptake can occur because the methanotropes do not prefer dry conditions. And then for nitrous oxide, we saw a little less in terms of seasonality. This was more dependent, I think, on the nutrient content. So for the purposes of this study, we did also do soil nutrient analysis. And riparian lawn, the site that comes out the highest here, had the highest levels of nitrate in the study and also total nitrogen. So we found that nutrients for nitrous oxide was a more dominant factor. But we did see, along as with methane, some higher fluxes in both spring and summer, meaning it may like more moist, slightly warm conditions. However, we did see that some of our heavily saturated sites had lower fluxes overall. And I think this could be due to these more consistently saturated sites allowed for complete denitrification to occur. And then overall, just to touch on the implications of the study, I just wanted to send home the message that suburban watersheds are important but often overlooked sources of greenhouse gas emissions. And that these emissions are highly variable in both space and time, so they're not uniform overall. And that finally, hydrology, temperature, and land cover have come together to jointly control these fluxes. And proper accounting of biogenic inputs is necessary to get an accurate urban and carbon nitrogen budget for the watershed overall.
Can you go back to your nitrous oxide flux? Are you taking questions now?
Yes.
Look at, so the stormwater swale, do you have some real like hot moments there?
Yeah. So that one's interesting because it is one of the sites that I've seen like pulling water in. So it is a riparian site, but there were times where it did have flowing water running through it.
Yeah, and you might expect the stormwater swells to be flashier because they're going to get some water. There's going to be some nitrogen in that water, and then they dry out. And um, these are great data. Boy, the whole you got a nice data set.
Yeah, it is interesting because I think also at the stormwater swale at one point, um, the stream gauge I think was something at like 9 feet. So it gets like really flashy hydrology at that site.
Could you go back to the methane? Sorry, I'm gonna
Yes.
because you made
Oh,
this
sorry.
interesting point that right. So your four sites on the left are the wettest, and they have high methane, and it is very interesting that they don't have high nitrous oxide. And I think you're right that if there's that there's just complete denitrification. Because look at the pond; it has no N2O. Go now. Let's go back to the N2O. Yeah, look at that really low N2O in that pond. And so yeah, I think I think you're right. The only way to confirm that would be if you're keen would be some N2 argon ratios in the water, which is an indicator of complete denitrification. If you wanted to do that, let me know. We could run them.
I have a question. Was there any frozen ground ever in that any of these places?
There definitely was. So there was some measurements that I couldn't take at the pond over winter. So there was frozen water there, and then the pond bank was quite frozen as well.
Great. It was a cold winter, I thought.
Mhm.
We had a lot of snow up
Yeah.
in State College, so
I think there was like a streak of like 2 months where I just couldn't get any pond measurements at all just because it was completely frozen over
Mhm.
and
Great.
There's been a
breaking
lot of
into
work.
it probably.
It's a good question. There's been a lot of work on freeze thaw effects on nitrous oxide emissions.
Yeah.
Yeah, that was something I could definitely tell as I'm trying to get the soil probe into the soil itself. In winter, it became a little bit more difficult around January, February.
And then your hands are cold and nothing works. It's no fun.
I do want to just chime in here to thank Gabrielle for braving lots of very cold and or very hot field work, oftentimes solo. And so it does look great to see all this data pulled together. Thank you, Gabrielle.
Cool. Thanks a lot, Gabrielle. Great presentation. Any other questions for Gabrielle before we pivot over to Chulin? Okay. Well, thanks again. Awesome presentation. And Chulin, let's pivot over to you if you want to get your presentation uploaded and ready to go. And just one logistical note, I have to jump off the call around 10:55 to get to another meeting at 11. So if we do go past 10:55, Chulin, I'll let you kind of finagle the questions and decide who to call on for questions.
Okay. Hello everyone. My name is Chulun. I'm a PhD candidate at Johns Hopkins, working with Dr. Scott Miller and Dr. Kirsten Kohler. Today, I want to introduce my work on methane in Baltimore, why we care about it, and how we are using a network of local sensors in the city to figure out where emissions coming from. Also, what practical suggestions for sensor deployment we could give to other cities. Why do we care about urban methane emissions? Methane is an extremely potent greenhouse gas. It's 86 times more powerful than carbon dioxide in trapping heat over a 20-year time frame. It's a major contributor to urban greenhouse gas emissions and global warming. The source of methane emissions in urban settings are diverse and often difficult to pinpoint, from aging natural gas infrastructure to emissions from landfills, from wastewater treatment facilities to residential usage and leakage. So urban landscape is a complex mosaic of potential methane hotspots. So how do we figure out how much methane a city is emitting? There are two ways. The traditional approach is bottom-up inventory. This method often underestimates real emissions due to its reliance on incomplete and outdated data. On the other hand, a top-down approach can provide a more accurate estimation by measuring atmospheric concentrations directly and inferring emissions. However, the fundamental problem is clear. Current top-down methods are neither too expensive for dense deployment or lack the resolution needed for urban-scale monitoring. We need cost-effective and continuous monitoring with high spatial temporal resolution for urban environments. Our local sensors offer a promising solution. They are much cheaper and easier to maintain. Here's a picture of Figaro TGS 2600. It's a metal oxide semiconductor sensor. It costs around $5. That means we can deploy lots of sensors across the city. The trade-off is these sensors are messy. They get interfered by humidity and other gases. Two sensors of the same type can give slightly different readings, and the readings drift over time as the sensor ages. So the local sensor give us coverage, but they don't give us accuracy out of the box. That's the gap our research is trying to address. The scientists from Solution for Energy, Air, Climate, and Health Center we refer to SEARCH designed custom multi-pollutant monitors with TGS 2600 sensor building to measure methane. The low-cost monitor also measure other 6 air pollutants and 2 environmental factors, temperature and relative humidity. This map shows the deployment of SEARCH network. Local sensors are co-located with high-precision Picaro cavity ring-down spectrometry at BSEC super site and 2 NIST tower sites, HAL and NEB. These 3 sites give us reference measurements at different heights and environments. The picture on the right shows us the physical setup of low-cost monitor at the top of a NIST tower. With the deployment of such network, we are able to study urban methane emissions in Baltimore. Next, I will introduce 2 projects I've been working on. Project 1 is about making sense of the raw data. Basically, we teach the local sensors to be accurate. Then we calibrate the entire search network in 2024 and evaluate whether the calibrated search network shows spatial and temporal patterns across Baltimore. Here's the problem in one picture. The red line is our local sensor measurements. The blue line is the co-located reference measurements. They should agree because they are measuring the same L, but actually they don't agree. They go up and down at different times. They don't even use the same units. The local sensor output is electrical resistance in ohms. The reference measurements is in ppb. So the raw signal is not useful by itself. We need to translate. We build a model that does the translation. We use a machine learning approach called random forest. We feed the model 5 pieces of information: the raw sensor signal, the temperature and humidity at the moment, concentration of other gases in the air, including CO and CO2, the sensor's baseline reading, and how long the sensor has been deployed because the sensor drifts over time. To train the model, we also give it reference methane. The model learns the relationship between predictors and the reference measurements and ultimately predicts the methane concentrations. When we train the model, we ask it, which of these predictors matters most? This chart shows the answer. The y-axis is relative importance. CO2 is the most important predictor as 100%, and everything else is scaled to it. CO comes in second, around 42%, followed by installation time and temperature. We see the raw methane sensor signal only has 8.8%, near the bottom of the list. What does this mean? The model isn't really reading or converting local methane resistance directly. It's learning the relationship between reference CO2 and the reference methane. CO2 is not an interfering gas to our local sensor. It acts as an indicator of atmospheric condition and, including CO2, significantly improve our model's predictive power. This figure shows model performance by season and by site. The pattern is consistent everywhere. Winter performance is dramatically better than summer. At BSEC, our ground level site, winter R square hits 0.88, which is quite strong. Summer drops to 0.04, nearly zero. Even across all sites, winter gets an R square of 0.72 and summer drops to 0.18. This seasonal performance variation makes sense. In winter, methane concentrations are higher due to natural gas combustion and infrastructure leakage. Also, the reduced mixing heights trapped emission near ground. Therefore, the sensor can detect more meaningful signals. While in summer, there's less methane variability that the sensor can detect. Now, let me show you what the calibrated network tells us about seasonal cycle in Baltimore. Each color line is one of our reference instruments, BSEC, HAL, and NEB. The black line is the average of sensor network across city. Methane is high in fall and winter, drops in spring, hits its lowest point around June, and rise again. All the reference sites show this pattern, and our network captures the same pattern. Why higher in winter? As we mentioned last page, higher natural gas usage and reduced atmospheric mixing. One thing to notice here is the black line is above the colored lines all the time. That's because the network average over the whole city. Most sensors are ground level and measure the higher methane concentrations in reference tower sites. We also generate a map showing methane concentrations across Baltimore. Each point is a sensor colored by its mean methane concentration over the study period. We do not observe a clear spatial gradient in methane concentration from the urban core to suburban area. We also examine the methane concentrations close to wastewater treatment and landfill. There are only 2 sites 4 kilometers within these sources. These 2 sites show slightly elevated concentrations compared to more distant sites, around 50 ppb. In a conclusion, our network can map spatial methane variability across the city and is most reliable in winter. However, the measurements uncertainties are relatively large comparing to the observed spatial variability. The observed spatial patterns should be therefore interpreted as preliminary characterization of methane distributions rather than precise concentration measurements. The calibration results from Project 1 raise a critical question. What level of sensor performance is actually needed for reliable urban methane emission estimation? This question drives Project 2. Well, I will determine performance thresholds for local sensor network through an observing system simulation experiment. In this project, we try to answer how good is the network? Can we trust it? Can we use it to reliably estimate emission across city? What if the sensors were better or we have fewer sensors? What should other cities learn from our experience? Let me explain how we find methane emission using our network. Step 1, the sensors measure how much methane is present in the air. Step 2, we use a transport model called STILT to trace air particles backward in time. It tells us where methane comes from before it reaches the sensor. Step 3, we use geostatistical inverse model. Inversion, it puts methane measurements and footprints together and asks which parts of ground must be emitting methane to explain what the sensors are measuring. The output is methane emission estimations across Baltimore. We tested 14 scenarios by varying 3 things. First, sensor error, low, medium, and high. Second, error distribution. We tested 3 errors with normal distribution, various errors that consistently off in one direction, and heavy-tailed errors. Third, network setup. Do we use sensor network or 3 reference instruments or both combined? For each scenario, we ask the same question: how close does the estimated emissions get to the true emissions we set? In real world, we don't have true emissions to compare with, but in this experiment, we use inventory as the truth. We try to establish performance threshold by comparing these scenarios to inventory. Since we have 14 scenarios and I did a lot of analysis, I'll show you some of my results. Here's my first finding. Bias matters more than sensor error magnitudes. Each arrow bar is one scenario. The height is half our estimates of Baltimore's total emission away from the truth. So shorter is better, represents smaller arrow. 3 colors represent small, medium, and high sensor errors. S2, S5, and S8 are biased. S10 is NIST towers only. Comparing S6 to S2, S6 has a larger sensor error, but S6 has a smaller relative error than S2. Why? Because S2 has bias, but S6 doesn't. A 1% bias in the sensor error can lead to a 3% increase in total emission estimation. And surprisingly, S10, it's the NIST-only scenario, has highest relative error. This indicates 3 reference instruments cannot map an entire city. Finding 1 was about the citywide total emission. The next question is, how can the network tell which parts of Baltimore emit more than others? Can we trust the spatial pattern? We zoom into grid cell scale. This chart shows how well our estimated spatial pattern correlates with the truth. The green dashed line is strong correlation. The red dashed line is moderate. With unbiased sensor error or low and medium scenarios sit above the green line. Large error scenarios drop into the moderate range even when they are unbiased. So the performance threshold for recovering the spatial pattern is sensors must be unbiased and their error must be small to medium. Once both conditions are met, the network gives us a reliable map of where methane is higher or lower across Baltimore. We've just seen the spatial pattern is recoverable at grid cell scale under right conditions. This chart asks a different question. Do the estimated hotspot top 10 percentile of all grid cells give us correct magnitudes? The answer is that even with perfect error-free sensors, that's S0 in the leftmost, the error at these hotspot grid cells is around 149%. Adding sensor error or bias only make it worse. This is the inherent limitation of inference modeling. It's not doing well in a grid cell scale. The third question is, how many sensors do we need? Is more always better? These 4 panels show how performance improves as we add more sensors, from 1 up to 42. The 3 lines are 3 different sensor error scenarios. The pattern is same in every panel. The curves flatten out around 30 to 35 sensors. After that, adding more sensors barely help. Looking at the top left panel for relative error, we notice that 3 lines that are at different floors, S8 above S5 above S2. That floor is set by the calibration and sensor quality, not the sensor count. So what actually matters is sensor accuracy, not buying more sensors. Pulling it all together, this is a summary of all 14 scenarios across our 5 performance benchmark. The left panel tells you which scenarios pass which benchmark. On the right, the bar chart ranks every scenario by its total emission relative error. Our current search network is biased with an error magnitude between S5 and S8. This means we can only trust the district-level spatial pattern. We know which districts emit more compared to others. We already have enough sensors. What we need is to improve the sensor quality. Other cities with calibrated sensor network could also pull out this table and figure out how much they can trust their emission estimation. So what should other cities take away from this work? We do establish some quantitative performance thresholds, and here are 3 deployment suggestions. 1, sensor accuracy matters more than sensor density. The biggest improvement comes from making each local sensor more accurate, neither by investing in calibration or by upgrading to better sensors. Buying more sensors of the same pool quality doesn't help. 2, target systematic bias and sensor drift. The question isn't how precise are my sensors, it's as it constantly run in one direction. And over time, even good calibration drifts. So cities need to plan for periodic recalibration. 3, deploy reference instruments as a supplementary to local sensor network. We know reference measurements themselves don't give us accurate estimation of total emissions across Baltimore. When we design a network, we don't want to replace these reference measurements. We should use them as co-location for better calibration and characterization of hotspots. Thank you.
So do you have any prospects for using, I'm trying to think, that's a great, wonderful presentation. And so, as you saw in Gabrielle's presentation, sometimes there's methane consumption. And I'm trying to think if these sensors would help us with methane consumption if you had them deployed along with height on a tower or real near the soil surface. Because so the soil is a sink for methane. It's a not going to say it's a super important term in the methane budget, but it's a significant sink. And I wonder, have you given any thought to how these sensors could help us to look at areas that are consuming methane?
Yes, that's a good way how we can deploy our local sensor network. But the most important thing here is how we calibrate. What we see from our current results is calibration is the most important thing. We do deploy many. We have 2 tower sites in Baltimore, and we use these tower sites to calibrate our local sensors. We found the calibration performance is very good at these tower sites, but on ground level, that's what you mentioned, like near soil, the calibration is terrible. The performance is terrible because on ground level, the methane variability is always lower and the local sensor detects less signals. That's why we cannot translate the local sensor signal into meaningful methane concentrations. So once we have better calibration for our local sensors, then definitely we will consider place our local methane sensors in near soil to study methane consumption.
You know where they could really help would be in landfills, right? So like in New York State and probably in other states, they're giving money to towns to collect to mitigate the methane coming out of landfills, and then they need to test to see does it work. And low-cost sensors would really because some of these landfills has very high concentrations of methane coming out of them.
Yeah.
And then you remediate them, and then the methane disappears, and the towns are struggling because putting up a flux tower it can be expensive and they're hard to run. These are exciting. You think about all kinds of things you could do with these.
Yeah, definitely. Like in those, the local sensor is good at detecting these methane peaks. Sometimes the sensor it will underestimate the peaks, but it's suitable for characterization of relative methane distributions. It knows which time period it has higher methane concentration compared to another time period. But overall, it does the underestimation all the time.
All right, I do see that we are at the hour. So thank you guys so much. Great presentations, lots of food for thought. Noticing John's great concept in the chat that we should integrate it all for an analysis. So I think that'd be a really valuable effort if people can pull it off. But yes, thanks again for participating. Good stuff. This has been recorded and it's going to be up online shortly for others to view. Have a great day.